Researchers have created engineered crystal structures that display an unusual physical phenomenon known as negative capacitance. Incorporating this material into advanced silicon transistors could make computers more energy efficient. Computers may be growing smaller and more powerful, but they require a great deal of energy to operate. The total amount of energy the US dedicates to computing has risen dramatically over the last decade and is quickly approaching that of other major sectors like transportation. In a study published in the journal Nature, University of California, Berkeley engineers describe a major breakthrough in the design of a component of transistors, the tiny electrical switches that form the building blocks of computers, that could significantly reduce their energy consumption without sacrificing speed, size, or performance. The component, called the gate oxide, plays a key role in switching the transistor on and off. The researchers have been able to show that their gate oxide technology is better than commercially available transistors. This boost in efficiency is made possible by an effect called negative capacitance, which helps reduce the amount of voltage that is needed to store charge in a material. The researcher theoretically predicted the existence of negative capacitance in the year 2008 and first demonstrated the effect in a ferroelectric crystal in the year 2011. The new study shows how negative capacitance can be achieved in an engineered crystal composed of a layered stack of hafnium oxide and zirconium oxide, which is readily compatible with advanced silicon transistors. By incorporating the material into model transistors, the study demonstrates how the negative capacitance effect can significantly lower the amount of voltage required to control transistors, and as a result, the amount of energy consumed by a computer. The researcher says that in the last 10 years, the energy used for computing has increased exponentially, already accounting for single-digit percentages of the world's energy production, which grows only linearly without an end in sight. Usually, when we are using our computers and our cell phones, we don't think about how much energy we are using, but it is a huge amount and it is only going to go up. The researcher says their goal is to reduce the energy needs of this basic building block of computing, because that brings down the energy needs for the entire system. State-of-the-art laptops and smartphones contain tens of billions of tiny silicon transistors, and each of which must be controlled by applying a voltage. The gate oxide is a thin layer of material that converts the applied voltage into an electric charge, which then switches the transistor. A negative capacitance can boost the performance of the gate oxide by reducing the amount of voltage required to achieve a given electrical charge. But the effect can't be achieved in just any material. Creating negative capacitance requires careful manipulation of a material property called ferroelectricity, which occurs when a material exhibits a spontaneous electrical field. Previously, the effect has only been achieved in ferroelectric materials called perovskites, whose crystal structure is not compatible with silicon. In the study, the team showed that negative capacitance can also be achieved by combining hafnium oxide and zirconium oxide in an engineered crystal structure called a superlattice, which leads to simultaneous ferroelectricity and antiferroelectricity. The researchers found that a superlattice structure composed of 3 atomic layers of zirconium oxide sandwiched between 2 single atomic layers of hafnium oxide, totaling less than 2 nanometers in thickness, provided the best negative capacitance effect. Because most state-of-the-art silicon transistors already use a 2 nanometer gate oxide composed of a hafnium oxide on top of silicon dioxide, and since zirconium oxide is also used in silicon technologies, these superlattice structures can easily be integrated into advanced transistors. To test how well the superlattice structure would perform as a gate oxide, the team fabricated short channel transistors and tested their capabilities. These transistors would require approximately 30% less voltage while maintaining semiconductor industry benchmarks and with no loss of reliability compared to existing transistors. The researcher says this work transforms negative capacitance from an academic topic to something that could actually be used in an advanced transistor.